For the summary of the day's proceedings, we have Professor Tom McLeish. Please, Professor McLeish.
Great. Well, Sam, thanks very much. And thanks, Joe, and thanks for inviting me here. I have the impression that those of us who are speaking, maybe those in the audience today, are a club of people who aren't quite sure why we're here, but we're learning during the day why we're here. And my son's a jazz trombonist. Our son's a jazz, and so he's taught me everything about jazz that I know, and I'm realizing that this is a kind of riff, a jazz riff on the theme, because I didn't know what I was going to say this evening right now until I heard what all the other speakers and all the great questions during the day were going to say. So I don't know whether it's a nice tune or not. We'll find out. But I've really enjoyed the day, and I just wanted to say thank you before I said anything else to all the speakers who've done a tremendous job, really interesting stuff, and to all the organisers too, very much. So here goes. Well, as promised, so I've got a few themes. I think I've 5 or maybe 6 themes. Quick, and we'll get some 10 minutes at the end. One is, we've learned a lot of this is, of course, history and philosophy of physics and engineering, I think. Isn't we've had. So the philosophy of engineering we've had from our resident engineer, but the point of the history of all these things is long. Now, of course, Mark knew very well that Snell did not invent Snell's law. In fact, wasn't it Feynman who said that the name one attaches to any scientific law is not the first person who's thought about it, but the last person who thought about it before it sort of got fossilized. But anyway, so Ibn Zal, this manuscript only turned up to Western eyes in about 1993 or 1996. I think it's Ibn Zal's first millennium treatise on burning instruments, and that's Snell's law in geometric form. It's the law of signs. There's the instant and there's the instant and refractive ray up there, and Ibn Zal then uses this as an engineer to make burning glasses that focus light perfectly. So it really brings all our themes together. But there's a name which hasn't been mentioned today, but I'm going to mention her name today because it's an Oxford and a British name, and it's probably the greatest natural philosopher you've never heard of, if you've never heard of him, but I'm sure all of you have, which is Robert Grosseteste. Robert Grosseteste is fascinating. He was the first liberal arts tutor to the Oxford Franciscans, right here where we are now, in the 1220s. And round about that time, he wrote quite extraordinary mathematical treatises on natural philosophy, on physics subjects, on sounds, on the sphere, on comets, impression of elements, and to our purpose today, wrote on colour and on rainbows. And so there's a project going on between Durham and York, where I come from, and Oxford, based at Pembroke College here, called the Order Universe Project, where we gather around astrophysicists and engineers and Latinists and historians and philosophers to read, translate and edit and comment on, from a scientific point of view, Grosseteste's manuscripts. So this is just to add a little bit of detail to what Mark actually knew about, but he cut those slides out, which I'm sure we're grateful for, but I'll put them back in. I was going to do, there we go. As an extraordinary conjecture Grosseteste makes in his treatise on the rainbow, which I've quoted, he gives colour 3 quantities: purity and impurity, clarity and obscurity, and greatness and smallness. So in his De Colore, he mathematically, in about 1220, describes a 3-dimensional abstract colour space for colour. There's absolutely no question about that. That's not conjecture, because he does all the combinatorics. What he then does is agree. Now, for tea time, I've understood Mark's colleague. A single rainbow does not cover the colours, the gamut of all colours. But Grosseteste makes the claim that if one considers all the set of all possible rainbows, which is a rather elegant and rather, physicist abstraction, almost mathematical abstraction, consider the set of all possible rainbows with, of course, all colours in all rainbows. Rainbows in different types of cloud, and rainbows illuminated by different colours of sunlight, redder light at the sunset. And for example, we have a 3-parameter angle, droplet type of cloud, and sun altitude, which can parameterize color generated by rainbows. So this project did precisely this. Now, we didn't do what Mark's colleagues done to measure the rainbows photometrically. We calculated them through atmospheric absorption, geometric optics, physical optics, and everything. This work was led by Hannah Smithson, who's a professor in experimental psychology here and at Oxford, I thought, and at Pembroke. And I thought you'd just, in case you didn't believe me that you get different rainbows from different types of cloud, you can generate this in your college backyard. Look, here's a generated rainbow with large drops near the spray at the top and fine spray at the bottom. And can you see that the larger drops give you more saturated colors and the smaller drops give you less because of diffraction, you see? So that immediately brings you in and out of the polar coordinate color circle. This is what Grosseteste is talking about. And here's a beautiful, now each rainbow, here's a section through the color diagram in slightly different coordinates. The A and B coordinates is what the experimental psychologists use. A single rainbow is that spiral. And rainbows with different droplet sizes give one this net of different spirals. And in a full 3-dimensional color space, the whole thing looks like this. That's a 2-dimensional complex surface. Oh, the spiral is because of the supernumerary bows. And you can see, I imagine, that when the sun sets and the whole thing gets redder, that net is dragged through, not quite orthogonal to its surface, but not parallel to its surface. So it is indeed the case that the set of all possible rainbows maps out a big chunk of visible color space. There's a paper of this in the Journal of the Optical Society of America, and the editor was absolutely delighted that reference 1 was R. Grosseteste de Iridae 1224, though had a little bit of difficulty finding it on the internet. But that's an Oxford flavoured thing. History is long here. Okay, history is long. Rainbow history is long, and I didn't think we should leave the rainbow without tipping our hat to, I think, the most extraordinary example of serendipitous double discovery. Namely, in about 1306 to 1308, both Kamal al-Din al-Farisi in Baghdad and Theodoric of Freiburg, who's a Benedictine monk, both had been reading, though it's not quite, the reason they did it at the same time is because they'd both been reading Al-Haytham, Ibn Al-Haytham. Well, of course, Al-Din had much before. Al-Haytham's great work, Optics, had just been translated into Latin towards the end of the 13th century. So the idea of building a camera obscura, getting your glass-blowing mates to blow you a sphere of glass modeling a rainbow, a raindrop, filling it with water, with a little bit of dust, and then doing the Newton thing that Newton would do for that famous prism experiment 350 years later, but in the more relevant to the rainbow setup of a spherical rainbow model in the first decade of the 14th century. That's what they both did. And here's Theodoric's diagram of the double reflection. There even also states he noticed double internal reflection, which would produce a second rainbow, fainter than the first, outside it, and with its colors reverse. Oh, wait. And isn't it lovely when a theory of physics not only explains what you were looking for, but gives you something else you weren't looking for? Echoes of Dirac there. Interesting, worth saying that the deeply entangled history of theology and science, particularly around light, hovers around all discussions of light, obviously. I mean, we should also tip our hat to that. Theodoric is explicit about this and names his inspiration for studying light as the extraordinary natural philosophical poem in the Book of Job, which I don't know if you've ever read it. It is not a religious campaign or anything. I'm just saying if you haven't read the nature poem in Job chapters 38 to 42, please don't let the sunset go down on you today before you have. It's an extraordinary Semitic, ancient Semitic essay on the importance of natural questions. There we go. Colour, objective or subjective? Well, so there are lots of examples of why 3D colors lives in 3 dimensions. We've seen the, in a beautiful resonance, these threes come everywhere. I've introduced the rainbow 3, which was implicit in comments by both Mark and Olaf, but there we are, the 3 cones in the retina. We've seen this, the red-green color cube. There it is again. Here's Grosseteste's color cube. But I just wanted us to make sure we all understood that color is not a function of frequency distribution or wavelength distribution. So Goethe is right about color being perceptual. Of course, Newton is also right, and Young is also right about being the physical generators of color being out in the world. I've got to the point at which I think actually those early theories of vision, you know, the weird extremissive ones, aren't entirely mistaken. Because now we know about Bayesian inference. If you think about perception as the entire perceptual chain, not just the eye, but the cortex is emitting visual priors all the time. And it's Aristotle, actually, who talks about the meeting of incoming rays and outgoing perceptual rays that I think gets closer to the entire psychophysical theory of perception. So which is the most pink of those 2 folders? I mean, this could be, it's the same color. Famously, you know, A and B have the same intensity. So your whole perception can be tricked all the time into thinking that things are unequal when they're actually equal. Keep your eyes fixed on the little cross in the middle. Keep them fixed. Don't move. Fix your gaze on that little black cross. Keep it there. Keep it there. Now what do you see? For whom have the little pink flashing things disappeared to be replaced by a green one going round and round? Okay. Now go back and check to see whether there's a green thing going round and round. No, it's not. Okay, there's nothing green. Oh, except if you think of green as negative magenta, then it's there. So sure, we can see negative colors, and here it is. But whether we see negative colors or positive colors depends on what we're adapting to and what our environment is, and depends how long you or she or he or I have been looking at this very famous color constancy figure. So let's remember how subtle color is. Yeah, isn't that gorgeous? I love it. There's been a wonderful light that music has hovered behind our day, as has a certain Anglo-German flavour. And here we move on to Ariana, who reminded us, and a particular Anglo-German family have been with us at least 3 points during the day, namely Wilhelm and Carolina Herschel, from part of the Hanoverian dynasty, which is why, you know, our royal family is still mostly German. You know, they only changed, it's only the name that isn't. And so there is, of course, this long Anglo-German history in both music and history, and indeed royal politics. There they are. You know, it's worth saying, Herschel himself, did you know Herschel wrote 25 symphonies? 3 oboe concerti, many oratorio. That's his manuscript of his goodness knows, and what, 12th symphony, I think, perhaps his 13th symphony. But it's also was the first astronomer to realize that aperture is everything, and yes, size matters. It's not the length, it's the width. Telescopes, folks. That's his famous 40-foot, actually it's like a 3-foot mirror. This was almost too big to be serviceable, though it did discover 6 satellites of Uranus. Behind all this music and physics dance has been, of course, there mention of waves. The quantum theory of light is the excitation, Claudia reminded us, the excitation of quantum fields, the vibrational oscillating excitation of vibrating fields. And this could be a violin string, or this could be 1 photon, 2 photons, 3, 4, 5, 6. It's a harmonic oscillator. I've been trying to think actually about how the musical aspects of William and Caroline she was a wonderful musician as well. She was a tremendous soprano performer. And then, of course, a discoverer of 8 comets, an extraordinary astronomer in her own right. How that musical substratum of their minds fed the creativity of their scientific minds. It's an open question, but I'd be really interested to hear your practical scientific philosophical talks on thoughts on how these interdisciplinary creative energies work at the level of real genius, which is what we're seeing here. I'm just fascinated by this. And no physics PhD course, apart from one that Mark and I are working on to our knowledge, actually includes, as a graduate school course, a theme on how to be more creative as scientists and more imaginative than you would be if you just stuck your nose to the grindstone all the time. Anyway, there we go. There's another theme of here we're getting a bit more philosophical, or maybe theo-philosophical. There's been this lovely theme of light and darkness, introduced by Olaf, negative light, but picked up again by Claudia, whereas the whole dark matter. So we've been playing with light and darkness, and there's resonance here. And I think we should be more. I think actually, HAP, we've had lots of history. We've had lots of physics. We've had quite a bit of engineering. I'm not sure we've had quite as much philosophy today as I was expecting. So let's chuck a bit in, or the history of philosophy, the history of the tension between light and dark, both actual physical light and dark and metaphorical light and dark, and theological light and dark. It was C.S. Lewis in his wonderful book, The Discarded Image, of the medieval cosmos, which I think presaged the work I later did with my medievalist friends on Grosseteste in a wonderful way, who pointed out that for the medievals, outer space was full of light. It was the realm of light, as Milton in Paradise Lost talked about the flight of Satan through the chaos of outer darkness and into our own cosmos. He calls them the happy climes that lie where day never shuts his eye, up in the broad fields of the sky. Space wasn't black, space was full of light. And so there's a historian of science, Vladimir Birlak at Durham, who's going around giving seminars on when space became dark. Of course, I'm trying to tell him that the sky being dark is about direction of rays. So you can have space full of light, as astronauts know only too well, at the same time as the sky being dark. And we've seen, so there's that, which is also a theme that's been running through our day, the polarization of the sky, the two-dimensionalness of the sky, and the three-dimensionalness of space must not be confused. But what the tension between light and darkness makes me think of is this great benefit of what the theologians call apophatic thinking, and how physicists in the last century have increasingly found this useful. It's when interpreting quantum mechanics, it is you're on far safer ground to multiply explain and articulate what an electron is not, than to try to say what it is. Claudia was wrestling with this, weren't you? Is it a wave or a particle? No, it's neither. It's a quantum thing and behaves mathematically in this way. But we're caught between a desire to be realists and an increasing burden that it's the path of idealism that is the one that one has to tread for the moment. And this idea of true illumination coming through darkness is a very old one and goes back to one of my favorite patristic thinkers. So Gregory of Nyssa is the most scientific of the patristic fathers. He's quite extraordinary. There's a wonderful treatise he has called On the Soul and the Resurrection, which sounds like a bit of crazy Christian theology, but its core is all about doing experiments of things you cannot see. Like the air in a bottle that one detects scientifically because of the water fighting its way in, and the fact that we know the moon is a sphere, not the projected circle. And he's arguing about the ability of the human mind to recreate a three-dimensional universe containing invisible substances. But as he gets more and more mystical, he becomes more and more fascinated by the way to truth being through darkness, which by which he doesn't mean evil, he means understood ignorance. So he says, what's it mean that Moses entered darkness and then saw God in it? What's now recounted seems somehow to be contradictory to the first theophany. In other words, if Moses saw light, now he sees darkness, how can he know more? Surely he knows less. For then the divine was held in light, but now he's seen in darkness. And what Gregory then goes on to say is that greater truth is eventually understood in this darkness. He calls it luminous darkness. What happens, I wonder, when we all start to think apophatically is the term about this. And then finally, of course, we get to Bill and the future of light. And I wondered about where we think what the future of our philosophical thinking about light might be. As our technology and science of light changes, so the meaning of the metaphor changes. I'm fascinated, for example, by the metaphor that runs through the ages of what we do as scientists. Or as natural philosophers, as we used to be called. One of the great metaphors for doing science is, quotes, reading the book of nature. It goes right back to Augustine, to Cicero. There's medievalists who talk about it. Galileo famously talked about the book of nature being written in mathematical language, and hieroglyphs. Robert Boyle talks about it. But the problem with all that, as in all metaphors, is that when the technology changes, the metaphor shifts too. A book is a very different thing to Cicero when it's a scroll that you have to read through, and everyone doesn't have a copy of the scroll, or to the early church invention of the codex, which is an extraordinary multiple random access technology, the best technology of information access ever, the best leap, hugest leap ever happened is from the scroll to the codex. But to ebooks, whatever. What's it? Maxwell said, commented on this metaphor of the book. He said, no, it's not like a book, it's like a magazine, because you can jump into any issue. Okay, so there's a problem with the book of nature metaphor. What becomes to the metaphor of light and darkness, or being good and evil, or truth and ignorance, or what we know and what we don't know? As light becomes more manipulable, more entangled, we could have said, as I think Bill mentioned, or someone mentioned, a little bit more about the vehicle of photon entanglement as the future of secure communications, but also fast communications, quantum computing with when light becomes not just that with which we illuminate the world, but that with which we compute and think about the world. Whoa, something might happen very differently with light. And one day, we get to go to Alpha Centauri, apparently. That's Alpha Centauri. Thank you very much for the day, folks. That's it. Bye.
We've got about 5 or 6 minutes for questions. In the center, please.
Just wait for the microphone so the people online can hear.
Thank you very much. Just to add another aspect to light, it's so-called the uncreated light. I just opened a discussion on this because you mentioned Gregory of Nyssa, and Gregory of Palamas in the 11th century speaks about uncreated light. He's not the only one, but he is the most known, which comes from inside. And I think everyone knows what I'm talking about when I say the light come from inside people and is reflected on their faces, but also if I look at what is now on the screen, we can see the light comes also from inside the universe.
Yeah.
Palamas is an important name in this discussion, and also I expected more philosophy today.
Yeah,
okay,
no, thank you very much. Yeah. So and I think that I'll just say one little thing that resonates with what I was saying. So the inward uncreated production of light, both its theological and anthropological resonance, we're increasingly understanding what that means as we understand cognitive psychology. And I think so the outward radiance of priors of the world that meet the incoming world, and so uncreated light meeting created light, if you like, being so reminding us that even perception itself is a creative act, which, by the way, Sam Taylor Coleridge knew all about that. But yeah, it makes me think of poetry. Yeah. Cool.
By the way, Elena Vasilescu from the history faculty, but I never did feel that philosophy, I doctoral philosophy, so I know something about this.
Great, good.
Next question with the Olaf, please.
Make up your minds, gentlemen. Yeah. That's all.
Professor Muller made my day by resisting metaphysics. But
I ruined it.
you questioned it, and you brought so much metaphysics. And you basically said science is ontological. But we heard today that its resolution, although they didn't say in this word, the resolution of science is evolving. I wonder how you could resist in front of this evolving resolution and bring so much metaphysical aspects to our modern evolving science.
Because I think the way we think about the world is four-dimensional space-time, if you like. Rather, I don't think we forget the past. I think the past, I don't think we fossilize the past, but I think it is important to recognize that the past informs our thinking, whether we are explicit about it or not. So the value that I would add to doing philosophy, I mean, the trouble with metaphysics is, as Olaf pointed out so well, metaphysics just means the book after Aristotle's physics. What else you want to make it mean is up to you. But if you ask me why do this metaphysics stuff and why read ancient authors when we've all got, we're all looking towards the future and we know what we know now, and they didn't know as much as we do. Well, for a start, I'm not quite sure that they didn't know as much as we do. They thought about things in different ways. But the point is this, that our concepts, our language, our metaphors are inherited from all this stuff. And I think it is better, I also think it's more interesting, I suggest it's more healthy to know how our thinking is going, to know what narratives affect our thinking. And to know which giants on whose shoulders we stand, sometimes forgetting we're standing on their shoulders because we're looking at the horizon. So I'm prepared to defend this. And by the way, you get to do new science. So the Grosseteste project, by the way, so here's a practical cashing out of what I said. When we began this about 12 years ago, when we as physicists started to work with the medieval scholars, because it looked like a bit of fun, right? And it was clear that these lovely historians of science could translate medieval Latin like there's no tomorrow. I mean, and the paleography of these hieroglyphs, we couldn't even work out whether it was a letter A or letter E. They could read this stuff right off. But the mathematics you need to understand what Grosseteste is saying about the cosmos or about colour, as stuff that we had. I mean, they were only good as Latin in today's educational system because they'd given up the maths when they were 13 years old. So you have to read this together. Now, what we hoped we'd be able to do is to generate, therefore, more accurate translations, editions, and more rounded commentaries of this work. What we didn't expect, and it's happened with every treatise, at some point someone says, like that conjecture, that Grosseteste says all colours are spanned by the set of all possible rainbows. Well, did anyone ever check that? No. Could we do it? Yes, we could. Let's do the calculations. That's happened not once now, but 10 times. So there's a whole slew of papers in Nature and Nature Physics, Journal of the Acoustic Society of America, I mean, serious journals, scientific journals, with new science that's actually a bit edgy and imaginative, that was inspired by helping our humanities colleagues to understand ancient sources. So I do it for the Nature papers, me, but yeah.
Great. Could you make it quick? All right. please.
Sorry, and I'll be quicker.
Thank you very much for this fascinating presentation. I wanted to connect to this fascinating stuff about the spiral representation of the colors of the rainbows. This is, I understand, simulated.
Yes, that's correct.
Okay.
It's all that simulated, yeah.
I wanted to share with you a startling experience which I had when we started trying to simulate the colors of the spectrum.
Yeah.
And what we did is we really run a good computer simulation of what gets through the prism and so on when it comes from the sun. And then it was calculated into our color space, and we compared it with the actual things that we saw. And this didn't match. I was quite shocked. It didn't match, particularly with the yellow. So the yellow, which was predicted by the machine, looked much more yellow than what you see in actual experimentation. And I'm very worried about it because I have the feeling there must be something wrong in the model, probably not in physics, but more in our representation of color space. But the yellow is a problem there. And I wanted to say that nice as though this representation is, it should be checked with the actual data, and there should be the measurements made.
Well, thanks to today, that's what Mark and I are going to do, because Mark, we're going to get in touch with Lee. No, your colleague who measures that. I didn't know that anyone photometrically measured rainbows, so we're going to check all this. Fantastic.
I'm afraid we're out of time for today, but there will be time to maybe have a chat a little bit afterwards. Let's thank Professor McLeish very much.